All right. And now this section here, we're on page 9, okay? And what we're looking at here are some things that are partly reviewed from physical science and partly new stuff. So we're taking the stuff you learned in physical science about the difference between ionic compounds and molecular compounds, and we're adding some new categories of information to that, okay? So the first category is conducting electricity when you dissolve these compounds in water. Okay, the ability to, what happens with conducting electricity when you dissolve ionic compounds and molecular compounds in water. Now, before we go too far in this, let me say something about molecular compounds. What does that mean? Obviously, it forms molecules. But we're talking about categories like ionic versus covalent and now ionic versus molecular. Molecular compounds are always covalent. Molecular compounds are always covalent, but not all covalent compounds are molecular. Molecular compounds are always covalent, but not all covalent compounds are molecular. Molecular compounds are always covalent, but not all covalent compounds are molecular. Okay? And it's kind of like we could use this analogy to that statement. All of you in this class are Dorman High School students, but not all Dorman High School students are in this class. Does that make sense? So it's kind of different categories when I say that. So molecular compounds are those covalent compounds that form molecules. And so there are some categories of molecular compounds that don't form molecules. Polyatomic ions don't form true molecules. They're molecular in structure, but they're not true molecules. And then there are really these things called extended arrays. My son, who's in the Army, just got his lieutenant stripe bars. Spent a tour in Afghanistan, and when you're in a war zone, you wear this plate on your chest. You have, it's not the same thing as a bulletproof vest. A bulletproof vest will stop a lot of bullets, but it won't stop certain kinds of bullets that are more armor-piercing type. These plates are designed to stop those really larger bullets that would otherwise go through a regular bulletproof vest.
Sniper.
Like sniper bullets. Well, unless you got a really, really big rifle, even those won't stop that. But this plate is actually covalently bonded together, but it's crystalline in structure. So it's not molecular, but it is covalent. That's just an example. You got a question?
One plate or is it a lot of plates?
I think they have a plate on the front and one on the back, if I'm not mistaken. Okay, it's a big plate that's actually wrapped up in the Nomex stuff, which is bulletproof material. So it actually is designed to shatter whenever it hits, and that absorbs all the energy. That's what it's supposed to do. But it's all, huh?
Still hurt?
Oh yeah. I mean, you could get knocked down and knocked back, a long way from it. So the idea is to keep the bullet from penetrating, but it won't keep you from breaking a rib, for example. Okay? All right. So back to this then. If you dissolve ionic compound, first of all, let me say this. Water is a molecular compound. Water is a molecular compound. It is not a good conductor of electricity. Okay? So molecular compounds, that's a good example. Molecular compounds don't conduct electricity very well. Okay? On the other hand, if you take an ionic compound like table salt, or like Epsom salts in that blue and white bag over there on top of those containers, or like calcium chloride, which you can buy this time of year to melt ice in your driveway. You take one of those salts and dissolve them in water, then the solution, the combination of the dissolved salt in the water, does conduct electricity very well. Okay? So if you're going to get hit with a lightning bolt, it's better to do it in a lake than the ocean. Really? And I don't know. Yeah, the electricity from a lightning bolt will flow across the top of a lake, but it flows through the salt water in the ocean. That makes sense? Because salt allows the water to conduct electricity. Okay? And the more salt you have, the more it does. Now, what about bath water? Because you probably heard if your hairdryer or radio falls in your bath water, it's going to kill you, right? Mm-hmm. That could happen. A lot depends on what's in the bath water besides just the water. Dirt, a lot of dirt contains ions, which will allow electricity to flow.
What about pee?
People do this.
I don't do that because you're sitting in your urine. You sit in your bathroom? Everybody. In the toilet.
Let's get back to chemistry, okay? All right. Another difference between ionic and molecular compounds is that ionic compounds will also conduct electricity when you melt them. Ionic compounds will conduct electricity when you melt them. Okay, so table salt, when it's just in the shaker, does not conduct electricity very well at all. But when you put it in water, the solution with table salt does conduct electricity well. Or if you melt the table salt, it will conduct electricity. Okay? On the other hand, molecular compounds, even when you melt them, don't conduct electricity. And that brings us back to water because water is a molecular compound and liquid water is already melted. That's a good example. Okay? All right, I'm flipping over now to page 10. And here we're talking about hardness. Hardness. Ionic compounds are most often crystals, and crystals are quite hard and brittle. So going back to table salt, if you look at the little tiny square crystals or box-shaped crystals of table salt, you can take maybe a knife edge or a spoon edge or something, you can crush it. It's really pretty hard. Okay? And when you crush it, it just shatters. Breaks up into tiny little pieces. Molecular solids, on the other hand, most often are a lot softer than ionic crystals. That's not always true, but most of the time they are softer.
What's an example of a molecular solid?
A molecular solid that would be like soft like that?
Yeah.
Let's see. Well, your skin. Your skin is made up of really large molecules called proteins.
Oh, you got proteins?
Your skin is made up of really large molecules called proteins. Okay? Most of the structural parts of your body are made of these really long organic molecules called proteins. Your fingernails, your hair.
I heard the fingernails and hair do the same group.
I don't know about that. It might be. It's possible.
So you're saying proteins, right? So what's the point of a protein shake? If you say proteins, your skin.
No, I'm saying proteins make up most of the structural material in any organic substance, plants or animals, or for that matter, bacteria. That's a whole different category. They're all made of proteins.
It's called protein.
Yes, protein shakes. Well, human beings don't make their own proteins. Okay, they have to take proteins from other sources and rearrange them into the protein structures they need. So that's the point. Whenever you do anything that's really strenuous, work your muscles a lot, you're breaking down the proteins in your muscles. So by ingesting new proteins, your body has the building blocks it needs to rebuild the proteins, and actually strengthen them, make them larger, include more in there. Okay. I'm not an expert in this, but it's my understanding that unless you're doing that kind of training, drinking protein shakes is not advisable. But I'm not an expert in that area. Okay. Am I right about that? Yeah. Yes, sir. Because if you're not doing exercise, then the protein becomes fat, basically. Your body breaks it down and uses it, and actually turns into fat that turn into the stringy proteins we call muscles. Okay? Muscles are really, really cool. They are proteins that whenever you put them into use, they climb up each other. They're really cool proteins. Yes?
Can they ever like stop growing like the muscle? Like could they ever like reach the maximum point at a certain time?
That's outside my area. I don't know the answer to that question. Okay. All right, melting points and boiling points now. Melting points and boiling points. Ionic substances tend to have very high melting and boiling points compared to the melting and boiling points of molecular substances. Ionic substances tend to have very high melting and boiling points compared to the melting and boiling points of molecular substances. Thank you. Okay? And we'll get into that in about Unit 6, I think it is, when we get into the theory of it. Okay? Basically, what holds the molecular substances together are much weaker attractive forces. Ionic forces have much stronger attractive forces. That's what causes this to happen. Enthalpy. Enthalpy, you can think of enthalpy as heat, but it really involves a lot of different kinds of energy. So you can think of it then as energy. Okay? But the particular kind of energy that's usually involved with fusion and vaporization is heat. Okay? It's just a larger term, a broader term. So when I say the enthalpy of vaporization, that's the energy it takes to turn it into a gas. So the energy required to turn something into a gas is larger. It takes a lot more energy to turn an ionic substance into a gas than a molecular substance. Okay? A lot less energy to turn a molecular substance into a gas than an ionic substance. All right? Fusion is the energy that you have to remove from something. You take it out to get it to freeze. So that's turning it from liquid into solid. So the enthalpy you have to remove from an ionic substance is much larger when you get it to go from liquid to solid than for molecular substances. Okay? So that's freezing. The opposite of freezing is melting. But the amount of energy is the same. It's just a matter of whether it's going in or out. Okay? So you could say the enthalpy of melting is much higher for ionic substances. It means the same thing because they're two things going in opposite directions. All about whether the energy is going into the substance or being taken out of the substance. Vaporization is the same thing as condensation. So when you vaporize something, you turn it from a liquid into a gas. When you condense it, you turn it from a gas into a liquid. The amount of energy is the same. It's all about whether you put the energy into it to vaporize it or take the energy out of it to condense it. Does that make sense? Okay? So ionic substances require a lot more energy to melt, require a lot more energy to vaporize than molecular substances. They give off a lot more energy when you condense it, the opposite of vaporization. They give off a lot more energy to fuse it, the opposite of melting, than molecular substances. Does that make sense to everybody?